Now that you've had some practice just proving things in the abstract about the permutations in prop, let's relate it to a computational notion of permutations. Way back on day 6, we defined a function is permutation of, and most folks seem to define that function by removing one element from the list as it worked down another. That's a great definition. I think it's one of the most efficient ways to compute whether one list is a permutation of another. But it's actually kind of hard to prove things about. That remove operation is sort of building up a tricky invariant. So it's actually much easier to prove something about a function that just computes all possible permutations, concluding with a final theorem that says, hey, if some L prime is in my list of all possible permutations, then it really is a permutation of the other list. So to do that, we've defined a helper function everywhere, which sort of puts a value everywhere in a list of lists. And then a function of permutations, which given a list of elements of some type A, returns a list of all possible permutations. You're going to want to spend some time with these two functions to understand what they really do. They've been written in a sort of Prof. Greenberg-ish kind of way, which is, ups and downs. So a thing worth looking at is, okay, what are the permutations of, say, ACT? And assuage yourself that okay, this really is all possible permutations of the list ACT. Double check that you really believe that's true. Now this works for any type, which is nice. 1, 2, 3, 4. Okay, not the nicest formatting there, but you can kind of check. You can see what's going on. Here, if I shrink it, maybe it'll be a little clearer what it's doing. Nope. Not any clearer. So you're going to want to spend some time looking at that and seeing exactly how it works. And then there's two lemmas. They're both pretty tricky, to be honest. They're going to take basically every kind of proof resource you've had so far. If there's a trick that you have to do, you're more or less going to have to do it here. I don't know if that's true for every possible trick we've seen, but it's close. These are going to require some lemmas, some of which were optional back from day 15 about in, and you're going to have to be pretty resourceful to see, how you can work with these maps and flat maps and so on. If you get stuck, ask on Zulip. Choosing exactly what you want to do induction on here is a little bit tricky. You're going to want to think about that a little bit too. So feel free to ask. These two proofs are a little bit similar, actually, in terms of the general structure. They both use slightly different helper lemmas. There's the other direction, too. So here we're showing 1/2 of the full reflection. So here we're showing that if something's in this list of computed permutations, then it really is a permutation. To really have reflection, you'd be able to go the other way. It turns out taking permutation LL prime and proving that something really is in this list of permutations is pretty challenging. So this is 5 stars advanced, optional. If it tickles your fancy when you're done with this file, when you're done with day 18, go back and see if you can make some progress on this. To really prove it, you're going to need to come up with your own inductive relations. You're going to have to define some tricky invariants. It's pretty cool what you need to do to get all this done, but it is not simple. So not for the faint of heart, but fun to try in any case. All right, give it a whirl if you like. These are required, but if you get stuck, aren't sure how to make progress, ask on Zulip. I think that seeing your way around here, this is a good test of are you video gaming? Because video gaming will not prove these. Or are you sort of following your nose properly? You know what the right way forward is. So if you don't know the right way forward, let me put you on the scent. Okay, that's it for now. Talk to you soon.